coming. Okay, as we've already said, this is actually the second part of probably the second meeting dealing with things to do with exponential asymptotics and resurgence at the Newton Institute. The first one was held, I hate to say, 27 years ago, when, although I didn't have much hair then, it was certainly not as grey as it is now. And that conference was a brilliant program in that it brought together lots of young people at the time who we kept the collaborations going and the connections going all throughout that time. What then happened in about a decade ago is that suddenly the string theory, quantum field theory people discovered the work of Carl and resurgence, and that was a big gave a big impetus to the field. That's led to a lot of work that has gone on since, and meetings that have happened in CERN and KITP. And around 2017, some of us got together and said, look, we've all got a next generation of people coming through. We should get them to meet and get them to talk. And that gave us the idea to run a meeting here at the Newton Institute. Obviously, things got a little postponed because of certain global events. So we started in a sort of a semi-hybrid mode last year. I think there were about 3 people or 4 people here in person. But then we were given the opportunity to come back and have another go this time round. So we've come here together to do that. This is the first meeting of 3 sort of set piece meetings that we're having. This meeting is obviously focusing more on the physical side of things. In about a month's time, there'll be a meeting on the more mathematical analytical side of things. And then finally, there'll be a wash-up meeting where hopefully we can present some of the new results we've got over the next couple of months, as well as identifying some problems that we all want to work on again in the future. So welcome to the whole program here. I'm very pleased that you can be with us at some point. So turning now to the first lecture of the day, Professor Sir Michael Berry was one of the pioneers of this field. Michael did a BSc in Exeter before moving to work with Robert Dingle, who again probably one of the fathers of the field of resurgence. Although Michael didn't work with him on resurgence at that time, it set him up in good stead for when later in working with Frederick or talking with Frederick Pham, Michael then the first piece of work he did in the area was to do with smoothing of the Stokes phenomenon there. After that, he went on to make many more contributions in this particular field, hyperasymptotics, for which I ended up with a PhD as a result, and lots of other things besides since. Obviously, Michael works on many things, too many to mention. He's sort of like the shock troops. He goes in and sorts something out and then moves on and does something else before people come along. But he's very pleased that he's agreed to come and give a talk today. And the talk that he's going to be talking on is one of the other aspects of his great contributions to science, and that's quantum chaology and the music of primes. So, Michael, please.
Thank you, Chris. There is a microphone for people remotely, but not in the room. Can you hear me? The back. Good. If I quieten down and let me know. And now, when I was invited to give a talk at this meeting, I sent a rather technical subject to do with asymptotics and of non-Hermitian matrices and in the context of polarization optics. But Ricardo wrote to me and said, we would really like you to speak about quantum chaos. Now, that's not a subject I've worked on for a number of decades. I was much involved with it in the beginning, but then not, and I went on to other subjects. And so I really hesitated, but I did find a talk that still works. Many of them don't work anymore when you go to, and I've looked at it and I made a few little changes, but I hope you'll forgive me, any of you who haven't heard this story. I think it's a good story, it's worth telling, but it's not my usual style. Okay, so this is a connections between quantum chaology and primes and Riemann hypothesis and all of that. And it's quite a complicated story, but I hope you'll understand. So, oh, now why doesn't this work, first of all? Yes, so you know, of course, what the primes are. I just can't resist saying that when I talked to school children many, many years ago, afterwards, a young guy came up to you and said, if you speak about this in the presence of mathematicians, don't include 21 on your list. So I don't anymore. Okay. Well, these are the atoms of arithmetic. And so let's look at how they behave. It's very convenient to look at the staircase of the primes. That's the number of primes less than x. This is the first of a number of different staircases that will appear during this talk. Well, when you look at very large values of x, the curve looks beautifully smooth, and this is well understood. There's roughly x on log x. But if you zoom in here, you still see the fluctuations, and these are what we want to understand. Okay, well, if you subtract the smooth staircase from the actual staircase, you get the fluctuations, this jaggedy music of the primes, as we will see. And here it is. Okay, now, why do I call it music of the primes? Because these fluctuations can be decomposed, and Riemann taught us this, into a series of locally sinusoidal functions. So if you take the staircase, it's a smooth staircase plus a series of harmonics. These are stretched out non-linearly, logarithmically sinusoids. And this impresses people. For example, Bombieri, can you read this? Yes, you can. I want to get rid of something. There's something on my screen that I can't get rid of at the bottom. Never mind. He wrote to me that the distribution of prime numbers can be so accurately represented in a harmonic analysis. It's exact, not accurate. Is absolutely amazing, incredibly beautiful. It tells of an arcane music and a secret harmony composed by the prime numbers. Now, the most interesting thing about series of harmony are their frequencies. You know, is it really music? If you play it, by the way, it sounds horrible. It sounds like random noise, but it isn't. Well, what are these numbers? Oh, sorry, why can't I? Yeah. So here they are, these frequencies, and these are the Riemann zeros, or rather heights of the Riemann zeros. Series of numbers, and here is Mr. Riemann. So let's talk about that. You have the Riemann zeta function. You all know what it is. It's a product involving the primes. You can expand it out and get a Dirichlet series of inverse S powers. S is a complex variable. Here is the S plane. Here it is. And here are the zeros being spoken about. And, oh, help. Why can't I get rid of that? Oh, help. I'm sorry, lots of things come that one doesn't want. Good. Oh, help. Why can't, good. Why can't this control? Just a second, excuse me. Yes, so this is, of course, valid when the real part of S is greater than 1, but you can analytically continue it in the various integral representations elsewhere. Now, Riemann hypothesis says all the complex zeros, there are some trivial ones elsewhere, but all the complex zeros lie on this line with real part 1/2. Now, that hasn't been proved, as you all know, otherwise this talk would have a different title. Here they are on the critical line, and the state of the art is that it's proved that the first 5/12 of the Riemann zeros lie on the line. There are infinitely many of them, and the first 10 trillion actually do. Now, that sounds kind of convincing. Of course, it isn't, and the reason it isn't is that these aren't such large numbers, because Riemannology is replete with logs and logs, and once you take a couple of logarithms, this is not such a large number. But anyway, of course, it isn't a proof. And even if 100% of them lay on the line, that still wouldn't be a proof, because there could be some measure zero off the line. So this is unsolved, and I want to describe some hints eventually towards understanding why. Now, once you take seriously the idea that these numbers are frequencies in music of the primes, a compelling question you ask, any physicist will ask, is frequencies of what? Well, frequencies of some vibrating system, eigenvalues of some Hermitian operator. This was envisaged in, well, mysteriously, because it was never published, but attributed to Hilbert and Polya in the 1920s. Right. Now, in this talk, the analogy with physics goes very, very much further, because it gives information about the interpretation of this unknown operator, still unknown though, detailed information about it, application to the distribution of the Riemann zeros, which was new to mathematicians, and feedback as a way of calculating quantum eigenvalues. Okay. You can think of it in the language of Donald Rumsfeld as a known unknown. You know, we know if Riemann hypothesis is true, there's this operator. If the Riemann hypothesis is not true, then we're in the world of unknown unknowns. You know, we're all at sea. I mean, you know, when I met Andrew Odlyzko many years ago, drove him from the station, he said, "Why do you physicists always believe the Riemann hypothesis is true?" And I say, "I don't believe it's true. I don't know whether it's true or not. There's some hints and I explore them, but in a way it'd be more interesting if it weren't true. Why would God be so malicious that she would give us this, all these hints about being true and then ultimately it isn't?" So, you know, I don't know. Right. So on the critical line, let's have a look at some Riemann zeros. It's very convenient if you multiply zeta by a phase factor, which will be discussed later. This is a real function on the line. It uses the symmetry of the Riemann zeta function. So here we are, the beginning, and here are the first few Riemann zeros. You go very high, zeros near the 10 to the 20th, measured in units of the mean spacing, and here you are, zeros are still there. It's observed. All these computations, by the way, detailed computations, including ones incorporating my theory, which I'll get to, were by Andrew Odlyzko, epic computations from the 1980s. So sometimes the zeros are very close together. This is called Lehmer's phenomenon. Here's a case where zeros near the 10 to the 18th, we have 1,000th of the mean spacing between two zeros, but still they're on the line. If ever the curve would miss, that would mean there were two complex zeros. The Riemann hypothesis would then be false. So they're all very close together. Now, this abundance of data about the Riemann zeros suggests looking at the statistics of the Riemann zeros. And one thing to look at is the pair correlation function. Near the 10 to the 20th, again Odlyzko, and that's the probability density of there being a zero at a distance x measured in mean spacings from another zero. And here you see there is some correlation. In particular, the data fits very nicely to 1 minus sine x on x. And this provoked Montgomery to conjecture that this is actually true for finite x and very high up. And there's a famous conversation with Freeman Dyson who said, "Oh, I know what this correlation function is. We have it in random matrix theory," which now I'll describe. It's the pair correlation of eigenvalues in the Gaussian unitary ensemble, which is the ensemble of n by n, large n, complex matrices, which are complex Hermitian matrices, whose Gauss distribution of elements is invariant under unitary transformation. It was developed for nuclear physics by a number of people, and for our point of view, most notably to a degree of perfection by Freeman Dyson. Well, look at another statistic. The spacings distribution, nearest neighbor spacings at P of S, beautifully fitted perfectly to the Gaussian unitary ensemble. So that provoked the conjecture that the Riemann zeros obey random matrix theory. But these are rather short range statistics. If you look at the abscissa on this picture, it only goes up to 3. So there are just 3 spacings. But there are longer range statistics which look at zeros much farther from many more means, but still tiny compared to the height where you are. And one of them is the Oh, sorry, excuse me, very important. Notice that there's this repulsion of levels. They're not independent random numbers. And the distribution is quadratic. This is characteristic of the Gaussian unitary ensemble. If you look at an ensemble of real symmetric matrices, you would have linear repulsion. Well, you clearly don't. Anyway, longer range. The number variance. Take a stretch high up where you would expect L zeros on the base of the mean spacing, on the average is L, and look at the variance. You won't get exactly L, the mean square deviation. Well, here it is. Now I'm now going up to 20. Now in the beginning, Gaussian unitary is a good approximation, but it deviates. And Odlyzko wondered whether he'd made a mistake in his numerics. He hadn't. We'll get to that. Okay, so this raises questions. Random matrix theory is failing when you look at longer range. So 2 questions. Why is random matrix theory so successful? And why isn't it? Why does it fail at longer ranges? So we need to answer both these questions, which we will. Here's our second staircase, the counting function of the Riemann zeros, the Riemann staircase. That's again, a smooth staircase. One knows the behavior. It's roughly not 1 over log x, but roughly log x or log t, and fluctuations. And the fluctuations, the imaginary part of the logarithm of zeta function just close to the critical line. Okay, so one knows, one can calculate them rather easily. Okay, now one wants to write the statistics in terms of this staircase. Well, actually the density, which is the derivative of the staircase. Well, you can. Here's the pair correlation. The number variance you can write also in terms of R zeta. And in particular, its Fourier transform, the form factor, as it's called, is a function of tau. And remember, all these x's are varied in terms of the mean spacing, which is known. Right. Now, these are all quadratic in the fluctuations, and that's the first important observation to make. And here we are again. This is what the counting function is. Now, I'm going to do a bad thing. Even though the product over primes is divergent in this region, still you can use it formally to calculate some of these statistics. Well, just if you expand it out, and you get a double sum over primes p and integers m, whose physics we'll soon see, and you include a few primes, and it sort of works. It gives you first few fluctuations. If you would carry on with this sum, eventually those fluctuations would diverge, and you would lose it. But it's not nonsense. Okay. Now, the point is that this resembles a formula from quantum chaology. Now, so for mathematicians, here's a lecture course of 1 page on quantum mechanics. Quantum energy levels are eigenvalues of Hermitian operators, and I'm using Hermitian and self-adjoint interchangeably. It's not an issue in this subject. Now, there are many types of Hermitian operator in physics, and particularly interesting and important are those of them operators where there's an underlying classical Hamiltonian dynamical system. Classical mechanics emerges, and this is a subtle question about which I've written innumerable papers, in the asymptotic limit when Planck's constant vanishes. So that's quantum mechanics. And for such systems, particularly interesting are those where the Hamiltonian orbits are chaotic. So and chaos, you know what it is. It's 1970s stuff. It's persistent instability, sometimes called sensitive dependence on initial conditions. And here's some examples. If you have a conical pendulum rotating, it's a nice regular motion. But if you have a magnet in the bob and you put 4 repelling magnets on the base, then you get nice chaotic. Now, why the hell does this keep appearing? I don't know why. I don't know why. It's gone. I don't know that either. It's a mind of its own. Good. This is quantum. Now, quantum chaology then there's a reason for that choice of word. I won't go into it. It's a study of the asymptotic dependence of quantum properties, in this particular case, statistics of energy levels, on the regularity or chaos of the underlying Hamiltonian orbits. And here's a conjecture that the Riemann zeros are energy levels of a quantum Hamiltonian system unknown, with a classically chaotic Hamiltonian counterpart also unknown. But the application of quantum chaology to arithmetic explains many fine details of the statistics of the Riemann zeros. And the basic ingredient, Gutzwiller, Selberg, Bailey and Bloch, developed enormously, by the way, by André Voros, who I saw earlier, is online here, is this: spectral fluctuations arise from the interference of classical periodic orbits. So I want to tell you a little bit about that. So the third staircase is the staircase of quantum energy levels. Right, counting function. And once again, you've got the smooth part and you've got fluctuations. And I'll outline the results of this theory. So you have a periodic orbit. Here it is. And they proliferate for chaotic systems. Here's one of them in the phase space. And here's a nearby orbit, different x. And locally, the deviation linearly is a little hyperbolic matrix, the stability matrix. Good. Now you need the action, that's the length of the orbit in the appropriate representation, whose derivative with respect to energy, you're looking at energy E, is the period. Now, here's the formula. Now, I'll just tell you where this comes from. It's a sum over these periodic orbits. It's a sum over primitive orbits and repetitions, and it involves some phases, which we'll get to, and involves the action, involves this matrix. It comes from this intuitively clear idea developed by Van Vleck, that if you want to calculate the green function, the propagator, time t, at positions x and x prime, you can asymptotically represent it in terms of all of the classical paths which link those events. And you take a Fourier transform, and it's all the classical paths of energy E that go from x1 to x2, usually a number of them. Now, when you take the trace, which occurs for the counting function, it's a trace of log of 1 over E minus H Hamiltonian. When you take the trace, you integrate over x, and using stationary phase as an oscillatory integral, this picks out the periodic orbits. This was Gutzwiller's massively important contribution from the late 1960s. Very good. Now then, thinking of long orbits, this determinant simplifies for the unstable case. The expanding eigenvalues dominate. Of course, they're expanding and contracting because of Liouville's theorem. The long orbits, and then these lambdas are the stability exponents, the natural quantities describing the instability in classical mechanics. And here's the formula. Now, here's the formula for the Riemann zeros. And one cannot fail to be struck, as I was in the 1980s, by the analogy between these two formulas. And there are analogies and also slight disanalogies, but still we persist. And I'll give you a little dictionary. You see, here's quantum and here's Riemann. Quantum, we have primitive orbits and repetitions. Riemann, you have primes and integers. And here you have the periods, multiples of the period of a primitive orbit, multiples of logarithms of prime numbers. The actions similarly, stabilities are actually all the same. It's uniformly unstable. The asymptotics, small h is like large t. Okay, there's an analogy and we can persist with it. And that's sufficient information about the unknown dynamics to apply the quantum theory we developed of spectral fluctuations. So let's look at the form factor. And I won't go through the calculus, I can't possibly, there's not enough time. Here's the form factor. Now, that's scaled time. and tau equals 1 corresponds in quantum mechanics to the Heisenberg time. That's time which is Planck divided by the mean level spacing, which is the derivative, inverse derivative of the counting function. That's a natural time. It's related Heisenbergly to the spacing. Good. Now, two properties. The statistics are bilinear in the spectral fluctuations, and so they're double sums over periodic orbits. And it's natural with any double sum in theoretical physics to separately think about the diagonal terms and the off-diagonal terms. That's the first thing. And the second is that the sums involve short orbits and long orbits, and these will give different types of contribution. So recall this contribution from a particular orbit. It involves this oscillation. Now, what this tells us is that an orbit with period t represents, I mentioned, a spectral oscillation with energy period Planck divided by t. So long orbits describe spectral fluctuation on small energy scales where random matrix theory is known to apply, evident, and the short, or observed to apply, and the short orbits describe spectral fluctuations on the large energy ranges where random matrix theory fails. This begins to be a clue to understanding. Now, the long orbits display a beautiful universality, and that explains the random matrix universality of the local level statistics, quantum chaology independent of details, and by analogy, the Riemann zeros. And this universality, you can describe it in words. It's a kind of phase-space democracy. If you have a chaotic system, the only conserved quantity is the energy. So an orbit lives on the energy surface. Long orbits, and this is the content of this universality, almost all long orbits cover the energy surface democratically with a microcanonical measure. Very natural idea. It's as chaotic as can be. It's ergodic on the energy surface. And this led John Hannay and Alfredo Osoro de Almeida to this idea that it turns out that the proliferation of orbits, they proliferate exponentially, is cancelled by the decay of their contributions because of their instability. And here's a sum rule. If take the limit of long orbits, and these are the Gutzwiller coefficients, and you have a tiny bit of smoothing of the delta function, those orbits with period t. This has happened again. I don't like it. Good. Oh, let's see. No, I don't want this. There, good. This is the Hannay-Osoro, and there are various counterparts in the mathematical literature, some more general, some less general than this. So this can be used for the long orbits and explains the random matrix universality. Well, okay, let's look at the contribution of the long orbits using this sum rule to the diagonal contribution to the sum. And it turns out, and it's a calculation, that you get, for this form factor, it gives you this linear behavior in tau. Now, that's the beginning of the Gaussian unitary ensemble form factor. So that's a success. And it's the first step in deriving the conjecture. We knew already in the late 70s, we already guessed that there was this connection with random matrix theory and chaos, but it was formalized and more generally expressed by Bohigas, Giannoni, and Schmidt, and this very celebrated random matrix conjecture. And well, what's the rest of it? Well, here's the rest of the random matrix Gaussian neutrons on. There's this interesting discontinuity of slope. Oh, help. How can I get rid of this damn thing? I don't like it. There. Well, what happens? Why does this fail to describe this horizontal part? Well, that's complicated because for that, you need the off-diagonal terms, also for the long orbits. We're dealing with universality. And the question is, how does this happen? Now, it's a very remarkable thing because what it tells you is that the double sum must somehow cancel this linear rise and replace it by this horizontal component, and that's a very subtle matter. I made some heuristic conjectures about it. There's been a lot of progress in recent years by Fritz Harker and colleagues, and it's a very subtle business how this double sum works. But what I wanted to do was to see it in operation, and you can see it with the Riemann zeros. And this is a calculation that I did. It's convenient not to look at this curve shape, but the integral of it. So, and I must say that Bogomolny and John Keating have extended the ideas to describe other statistics all around it, but they're not all quadratic in the fluctuations, of course. Some of them involve higher. Good. And in particular, look at this phase. I call it a phase transition because it's a result of subtle interference involving the periodic orbits in the double sum. Involves the correlation function of periodic orbits. So here's this integrated form, but it's tau squared, but then it becomes linear. So I looked at it for the Riemann zeros. Okay, and for the Riemann zeros, this double sum involves primes and multiples. It doesn't matter what the details are. But here's the variable tau, and here it is. And I looked at a particular stretch, and here now, what is this? It's this integral of the pair correlation. Here's what you get if you just have the diagonal sum. You see these crosses, which quite closely approximate the random matrix theory double sum, which of course then continues all the way. Sorry, diagonal sum. But if you then calculate the double sum, then you find you get this beautiful agreement. It cancels off. It's still rather mysterious that it happens for the Riemann zeros, but it does. Cancels off the quadratic rise and replaces it by something. So it's a good hint that things are working well. So the deviations from random matrix theory require contribution from the short periodic orbits as well, but they're not universal. Okay, they differ from system to system. So we begin to understand why random theory works and why it doesn't work, and let's put that to the test. So here's the picture I showed you earlier. This is the Gaussian ensemble differing from this is yet randometrically differing from the data, the dots, but now the smooth curve that joins them is in fact the contribution, is in fact the contribution from the short orbits. It's Gaussian time the short orbit. So this is really working. Let's go further. This takes us from 2 or 3, where random matrix theory works, begins to fail up to 20 mean Heisenberg mean spacings. And let's go further, let's go to 100. Now the curves are completely different. Random matrix theory is lost in the beginning, still agreeing perfectly, at least almost perfectly. I wondered whether these little random deviations were noise in the data. You can't see very clearly, but there are 2 curves in these pictures. Yes, you can just about see. Well, let's go on to 500,000 mean spacings, which you can do if you've got 10 to the 20 zeros, still working. So this is random matrix theory failing, and this is a strong suggestion that quantum chaology really has something to do with this problem, because it shares the property of random matrix theory locally and deviating because of the short orbits not. Now, this theory was based on, as I said, the Gaussian unitary plus a correction, and I've shown you the correction from the short orbits from the diagonal sum, and the Gaussian unitary coming from the long orbits. It's a sum. Now, that's what I calculated. What I didn't realize is that you can sum it actually, and John Keating and Eugene Bogomolny summed it, and so did Fuji independently, and there's an amazing fact about it. You see, this is the pair correlation and contribution to for very high Riemann zeros. But look, it involves the Riemann zeta function itself, not on the critical line, it's not a half, and this variable is x divided by the mean spacing, so it's a local thing. So this is an amazing, now using the term to describe this conference, this is an amazing spectral resurgence. The low Riemann zeros appear as resonances in the statistics of the high Riemann zeros. Well, let's look at them. I showed you the pair correlation. And before, I showed you this part. This is what led Montgomery to his conjecture. But you go further, and here you see the first resurgence resonance. Good. So now let's look back again at these calculations of the number variance I showed you before. Now one knows what these peaks are. These are the resurgence peaks at the first, second, and third Riemann zero. So it's a wonderful thing. So we understand this beautiful resurgence is appearing. Now, there's also a correction from the short orbits for the off-diagonal sums, which I didn't include. But when, and you can calculate it, the sum product over primes, again, it involves this Riemann resonances, and this is Bogomolny and Keating, and that describes those little oscillations that I thought were, will help. Little oscillations down here, which I thought were noise in the data. No, I can't show you a reproduction of this exact situation, which is zeros near 10 to the 12th. But they looked at zeros near the 10 to the 9th, and this is an analogous, but it works beautifully. So all these features of the Riemann zero statistics are described by this idea that there is some classical orbit, classical dynamical system, which has various properties I'll come to later, whose eigenvalues are the heights of the Riemann zeros. It works beautifully. Good. Now that's an intellectual current flowing from quantum to Riemann. But let's go the other way, Riemann to quantum. There is something in the literature discovered by Riemann, this amazing formula which is universally used in computation of the Riemann zeros with some developments. It's called the Riemann-Siegel formula. And this was discovered by Riemann and buried away. Nobody for 60 years really appreciated it until Siegel looked at Riemann's Nachlass, his collection of writings, and realized that Riemann had the most amazing way of actually calculating the Riemann zeros. And if Siegel hadn't rediscovered this and developed it himself, we may even now not have it. So this is Riemann's notes, a very chaotic writer. It's hard to disentangle, but Siegel realized there was something there which wasn't understood and which I want to tell you about. Now, this approximates this real function on the critical line, and now I'll tell you what this theta is. It involves the argument of a gamma function of a quarter plus a half IT, of which more later. Well, Riemann's way was amazing. I've written a little expository article about this. It was a fiendish application of his newly discovered, newly invented method of steepest ascent to an integral on the critical line, to this representation of Z of t. Now, we all know what the method of steepest ascent is. Actually, it was anticipated by Stokes 40 years before. He used it to calculate they pre-invented the method to calculate the asymptotics of the Airy function in its oscillatory region. By the way, he pre-invented the WKB method to calculate asymptotically the Airy function for positive in its decaying region. Never mind, Riemann was much more general. Now we know it. You have an integral which has some saddle points. Locally, you can approximate in the exponent, approximate by Gaussian, and on you get corrections. We know a number of refinements now. For example, if the saddle points, when you change the parameter, can come together, you get what we call diffraction catastrophes. Instead of exponentials, you get Airy functions, Pearcey functions, and Chris and I found the high orders of such expansions, also the beginnings of asymptotics. Also, if you have a saddle point in conjunction with a pole. But Riemann's first application was something that even now we don't use. It's where you have a saddle point in conjunction with an infinite string of poles. Very beautiful, amazing thing. Anyway, he did it. And the physicist way is you can formally manipulate the Dirichlet series, which of course is not convergent for it, but still you can. And you can get the same formula Still hard work, but much less than Riemann's way. And here it is. So it's a sum of what looks like the terms of the Dirichlet series and their complex conjugate. This is a real function, up to some n star, plus a series of corrections. And n star, this is called the main sum, and n star is the integer part of the square root of t on 2 pi. So more and more terms, the higher you go, but only growing as root t, so modest. It's still hard when you've got 10 to the 20. I mean, that's what Lisco had to develop special routines for doing calculations to calculate even the square root of 10 to the 20 terms, but he did. Now, just to give you a hint, if you take the Dirichlet series and you take the first n star terms, and then you take the complex conjugate, if you take the Dirichlet series and subtract off the first n star terms, you get something that depends on n star, and it's the asymptotics of that expanding about the limit n star, which gives you these corrections. Now, the first term gives remarkable, very first term of the main sum, cos theta of t equals 0, gives you zeros with the correct asymptotic density, because this gamma function asymptotically has the logarithmic behavior, and it gives you immediately the correct Riemann zeros according to the mean density. And what the higher terms do, and the corrections, is they shift these Riemann zeros into their correct random matrix theory locally and globally not positions. Good, so here are the corrections. Now, they involve something else. They involve this same quantity, but not the integer part, the actual value, square root of t on 2 pi. And just to tell you, this z is the deviation of this in a particular representation from its integer part. That's also, it's very refined information, because the main sum itself is discontinuous. What the corrections do, one by one, they remove the discontinuity of the different derivatives of the smooth function z of t. Okay, so here's what this little z is. You're going from two nearby integers, neighboring integers of root t on 2 pi, and this tells you what happens in between. It's a curious awkwardness of notation. It doesn't matter. That goes from -1 to +1, and that's what this z does. So that's what the Riemann-Siegel formula tells you. And these coefficients are a playground for modern asymptotics. Gabka and Siegel calculated them. The 0th one is this function of z. In spite of appearances, it's a entire function, because the poles of the poles of the bottom are cancelled by the zeros of the top. It's not obvious. And here are the first few: Riemann, Siegel, Gabka. I needed more, and so here's the 20th one, and they're all derivatives, and you have to be careful when you plot these on the computer, but you can. And then the question is, what are the high orders? What is this series like? And at that time, Chris and I were looking at high orders of expansion, following Dingle, original idea for some of the more standard special functions. And it took me a year to work out what the high orders of this series are. And basically, here they are. The high orders behave in the way that we're all familiar with: factorial divided by a power, and there's there's this a on the bottom when this is incorporated into the Riemann-Siegel formula. But it involves a decoration f, which is unique to this function. And here's the decoration. It's actually involves theta functions, and these are convergent sums, which involve this z. So how good is this? You have to check this, and that involves coding up all these high orders of expansion. And here you see the curves label different values of Z, and these are different orders of expansion. They're different for even and odd orders, and here the exact, and here's the asymptotics, and you see you capture the behavior. Not perfect, but it's good enough. So now one has this formula. One can the high orders, one can do Borel summing of the tail and estimate the error you make if you stop the Riemann-Siegel series at its smallest term, which, by the way, you never need to go that far in all these detailed calculations of the Riemann zeta function. So here's the series again, but you're stopping at a particular term. You're truncating this series. And the least term is the integer part of 2 pi t. So that's, you need a lot of terms, more and more terms. You see, it's only square root t in this series, but to take this to its least term, you have to do a bit more work. And you can get the error estimate, you Borel sum, knowing the high order behavior of this series. And you stop it somewhere at this smallest term, and the error is equal to e to the minus pi t. Now, that suggests something. You know, we all know is small instantons, and these complex periodic orbits whose periods are multiples of pi. That's like the harmonic oscillator. We'll come to that in a little while. Good. Now, by the way, even for the first 0, 14, you have only one term in the main sum, but you have a series of corrections nearly near the least term goes back to the 90th, 90 terms of these corrections. So you never need to go that far. E to the minus 2 pi times 14 is an error smaller than in any of the numerical calculations of the Riemann zeros so far. Okay, now there is, however, something a little bit unsatisfactory in having the main sum, which has these discontinuities, then have to be subtracted off. So John Keating and I realized that you could, at the price of introducing an extra parameter, you could have a smooth version. And the natural way, this is again a series of sums over primes and integers. So now it's the following: the leading order, okay, the smallest, involves an error function which smoothly cuts off, and the k is the smoothing, and what the variables are, I don't need to go into it, but anyway, it's a smooth version of this one. And you get the correction terms involve, again, something with difficulty, but you can calculate them, and it involves these functions b of t, which you have a generating function for them. Where have I got? Yes, you have the generating function in terms of these incomplete gamma functions psi. You can calculate all of this. I'll just show you how it works. Right, here near the beginning. Now, this is the Riemann zeta function going through its 0. The main sum, involving just the first term of the main sum, well, the main sum only involves one term, you miss a little bit. But if you take the leading order of this Riemann-Siegel lookalike, as we call it, with the smooth, it's rather good. Go to near the next 0. That's where the main sum has a discontinuity. And here's the Riemann 0 near to 25. And here you see this tiny deviation. That's this lookalike formula. And if you go higher, there's a place near t equals 200, where the Riemann-Siegel main sum would predict a violation of the Riemann hypothesis. There it is, you would miss, it's the corrections that put it right. But once again, our Riemann-Siegel lookalike is almost indistinguishable, and you don't need any of those corrections. So the natural suggestion is, with this, that you can apply this to quantum mechanics. And there are several Riemann-Siegel lookalike formulas involving periodic orbits and repetitions for something which is much nicer to calculate than the staircase. It's the quantum spectral determinant. That's the analog of the zeta function, which has eigenvalues of zeros. It's det of E minus h, basically regularized. It's this thing. So So and that you can compute, of course, and then you can compare. You expand it because det is e to the trace log, and trace log involves the counting function. You can use all the previous theory and test it out. So and then you've got a periodic orbit sum, but because of the exponential, you have not only periodic orbits and the repetitions, but you also have what we call composite or pseudo orbits, which are combinations of periodic orbits and their repetitions, integers in combinations of primes and their and products are just integers, and that's what occurs in the Dirichlet formula that we started. So the analogy is clear, and this resolves a lot of convergence difficulties with the original sum, because it's a finite sum. It goes up to the Heisenberg time, and you get this periodic orbit representation of the spectral determinant, as I say, and the zeros quite accurately represent quantum energy levels. And John Keating and Martin Siever looked at a particular system, the hyperbola billiard. There it is, the orbits in bouncing orbits. It turns out, although it's an infinite system, it has a discrete spectrum, and you can calculate. And they did. This is just one of their pictures. It's the spectral determinant, which has its zeros at the energy levels, rather nicely semi-classically approximated by the by this Riemann-Siegel lookalike. So that's something that goes in the intellectual direction from Riemann to quantum. I'm not sure it's a terribly useful way of calculating the quantum energy levels, but it's a way. And why I say I'm not sure is that there hasn't been a study of the algorithmic complexity of different ways of calculating quantum. There's a lot of work on matrices and complexity of calculating the eigenvalues, but would want to compare that as the work you have to do to calculate the up to asymptotically large energies, to calculate the effectively calculate the energy levels with an error which is small compared to the mean spacing, compared to this Riemann-Siegel lookalike formula. So that is, I don't know if it's useful or not, but it's a nice connection. So now, in the last minutes, what about this unknown Riemann operator? I'll tell you what we know about it. It has a classical counterpart, corresponding to a Hamiltonian flow or some symbolic transformation, symplectic transformation on some phase space. It's chaotic, that is unstable and bounded. It doesn't have time reversal symmetry. That's because of the complex Hermitian rather than real symmetric. There's an anti-unitary symmetry. It doesn't have an anti-unitary symmetry. It's uniformly unstable. All the divergence exponents are all the same. They're all unity. The classical periodic orbits have periods independent of energy, which are multiples of logarithms of prime numbers. In terms of symbolic dynamics, the Riemann dynamics is peculiar. It's a bit like Chinese. Each primitive orbit is labeled by its own symbol, analogous, namely a prime, in contrast to the usual situation where periodic orbits are represented by words made of letters in a finite alphabet. So, for example, in a billiard, in a polygonal billiard, you can specify the sides that a periodic orbit reflects from before it closes, and there are analogues of that. So, but here it's much simpler. One primitive orbit is labeled by its own symbol, namely a prime. Now, there are these phases. You may have noticed this minus sign. There's something weird about this, which exercised Alan Kohn quite a bit when he read about it. The Riemann, these phases are all pi. Now, in the sinusoids that give you the contributions, you get the phase m times the mass of energy. Now, it's not clear, of course, if a phase is pi for a primitive orbit, it'll be 2 pi for even numbers of traversals. but that seems not to be the case. So that's a peculiar thing, okay? And it possesses complex periodic orbits. That's from this exponential tail of the correction Borel summed of the Riemann-Siegel formula, whose periods are multiples of pi. And for the Riemann operator, the leading order semiclassical mechanics is exact. So it's obviously some simple, like the harmonic oscillator or the Kepler problem. Semiclassics is exact. You don't need corrections, and it's quasi one-dimensional. You get that from comparing from the power law behavior of the mean spacing of the zeros. So here's a speculation that we made about the Riemann operator with eigenvalue correspond to heights on the critical line. And it's absurdly simple, and it hasn't worked yet, but it works to some extent. And it's this is with John Keating, and this is just XP. That's the classical. We quantize in a little while. Okay, now, first of all, this does have a repeller, so it's unstable. Of course, it's not persistently unstable because it's an infinite system. We would want to close it somehow. Okay, well, one naive way to close it, so it breaks time reversal symmetry as well. This is good. It's linear in P. Oh, help. Yeah. So let's look at the counting asymptotics. Let's see if it's anything like the mean level spacing. Well, you've got to cut it off somehow. And a natural way to cut it off is with a phase space cell of H bar. Then the area of this cutoff, I'll show you in a minute, divided by Planck is the counting function, is the mean, is the smooth counting function. And here's a very natural way to cut it off. You have a size H bar, a square, and it doesn't matter whether it's anisotropic. It's just the products of the X and P squared are is H. And so you look at this as a finite area. Now, when you calculate, you get basically E log E minus 1 plus 1. Now, that's good because that's if H bar is 1, of course, or 2 pi, I can't remember. That's the counting function of the Riemann zero. So it seems to work, but you can do better. See, with the harmonic oscillator, that's a nice, or any bounded potential, you can have you have basically a loop in phase space, and topology and some asymptotics and geometric phase business tells you that as you go round this loop, the evolution goes in one direction, and you acquire a phase of 2 pi, which is what gives you the n plus a half in the harmonic oscillator. But here, you only have a pi on 2 rotation, so the analog would be minus pi on 8. And when you put that in, you get this amazing thing, which is the first 3 terms correctly of the expansion of that gamma function that gives you the mean counting function of the Riemann zero. So there's obviously something nonsensical about this. Okay, here it is, the first 3 terms of the counting function. Here it is. Now, and once again, this inverse gamma function. Now, it's tempting to say, well, maybe a first approximation to the Riemann operator is just would just give these zeros correspond to the zeros of cos theta function, because that's what this mean smooth are. Well, that doesn't work actually, and it doesn't work for this reason, that it doesn't work because it does give you along the critical line some approximate Riemann zeros, which we know later have to be corrected. But unfortunately, this has zeros also also along the real axis of the Riemann zeta function, not just along the critical line. And even worse, there are complex zeros. So off the line. So these are the ones you want. There's a bad one near the origin. So this doesn't work. You mustn't think of this smooth function as corresponding to a Hermitian operator, which is the first term of some series that will give you the unknown on it. It doesn't work. So let's go back to XP. well, you would like to symmetrize it, to make it quantum. So you do that, half xp plus px, that's good. And then you get the eigenfunctions, so functions of position, which are 1 over x to the half, and it involves this phase factor involving e, which is the t, okay? And then calculate the momentum eigenfunction, because you see this is symmetric in x and p. So when you calculate the momentum eigenfunction, it's a similar behavior, but it involves this gamma function that we've encountered before. So it's natural to write this symmetrically. Here we are. There's a lovely duality between the position and the momentum states involving this same quantity theta, which appears in the counting function to make it real. So some physical significance of it, which is another nice hint that we're not doing something that's completely nonsensical. Now, we've tried closing the system by making various identifications. You can identify p and minus p, x and minus x, and then again, it doesn't work. We haven't had any success with that. But let's look at the symmetries of this operator, which are in for example, in condensed matter physics, the translation symmetry plays a crucial role. It's central to understanding the structure of electrons in solids. Well, dilation is one symmetry. It's invariant under that, and it has a nice effect on wave functions. If you function multiplied by k is the function not multiplied by k, operated on by this evolution operator, which involves the this conjectured Hamiltonian. So that's it's the evolution with log k gives you the dilation. That's a nice observation. Then there's something else, which is you can exchange x and p, and to do that you have to be a little bit careful, but you can. And the effect on wave functions is also known. I mean, I'm not going through the details of that, but that suggests that if you want to make a wave function which reflects all these symmetries, you should add together all the symmetrically, I mean, sorry, with no phase factors, all the symmetry translates of the initial wave function, just to say you could do it with a phase factor. That's the analogy in mechanics of, in quantum physics of solids, of the Bloch quasi-momentum, which labels the different states. Here, the idea would be if you introduce phase factors, you would get, in this dream that we have failed to develop properly, you would get the zeros of the other Dirichlet L functions, not just the Riemann, of which the Riemann zeta functions are simple. They all obey a Riemann hypothesis, but that's there. But you just add them together. So you imagine there's this quantum condition. Now, actually, when you work it all out, you get precisely this function z of e returning. But of course, the Riemann zeros are where it's 0. So these are places where, not places which are eigenvalues, but places where you don't have eigenvalues because you can't create this superposition of states. And this reflects what Alan Kohn had thought, which he said, maybe this minus sign means that the Riemann zeros are the condition for non-eigenstates. Now, of course, this is nowhere near a proof of the Riemann hypothesis. There's nothing that says that with Hermitian operators, places where you don't have eigenstates must lie on a line. So that doesn't work, as Alan Kohn well knows, but still it's a hint. And you can write this in a nice way, actually. You can write it as symmetrically in x and p, where x and p are related by Planck, and it's these two separate expectation values of with x representative of the state and the p representative of the state, with a little change of signs. That's what I call a pregnant formula, but what would be the issue of the pregnancy, we don't know. So you know, at the end of all this, we learn what Pete Hines said: problems worthy of attack prove their worth by hitting back. I can't resist telling a story. I visited Caltech in 1985, the beginning days of string theory, great excitement. Indeed, the president of Caltech apologized to me for not coming to my colloquium because he had to go to Palm Springs and explain string theory to President Reagan. No comment about that. Anyway, I met John Schwartz, one of the early two protagonists, Green and Shaw, before Ed Whitten became involved. And he said, "What are you working on?" I said, "Oh, I'm working on connection between the Riemann zeta function and quantum mechanics." "Oh, yes," he said, "we've got lots of zeta functions in string theory. I expect the Riemann hypothesis will be proved in a few weeks. It'll be a baby exercise in string theory." Well, 30 years later, I met him again and I reminded, he said, "Did I say that? We were very enthusiastic in those days." So we're still waiting. Now, I'm not going to give, because my time is up, I'm not going to give the last part, which is just a bit of fun. It's about a way in which you could observe the Riemann zeros in optics. And it's just this, that if you have, there are a lot of functions proportional to the Riemann zero, to different whose Fourier transforms are known. And if you start this out as the phase distribution of a wave, it's of an antenna, its far field gives you side lobes whose zeros, they're called cones of silence, are the Riemann zeros. So it'd be a way of observing the Riemann zeros in optics. And there have been a few papers developing that idea, but I don't want to go there. I want to go to the end. So let's go to the end now. There. So we have this two-way intellectual traffic linking apparently different sciences. So quantum goes to Riemann. We've got this strong hints about the Riemann zeros being eigenvalues of some quantum operator with a classical chaotic counterpart, which we don't know, but we know things about it, involving the primes. Accurate description of the statistics of the Riemann zeros. And then the other way, there's this way of Riemann-Siegel lookalike, various different semi-classical ways motivated by the Riemann-Siegel formula and its smoothing to calculate quantum energy levels. And in the past, and I mean the past, I've written a number of papers about all of these different aspects that I've spoken about today. So thank you very much for your attention. Thank you.
Okay, does anybody have any quick questions?
Now, I don't hear very well, so I might ask Chris to translate, but I shall do my best.
So in the beginning, you mentioned that there was this, so you plotted the number of primes.
Yes, counting function.
Yes, a counting function.
Staircase.
So then you looked at it was like x over log x.
Exactly.
So then
Go back to Euler.
Yeah, and then you said, well, you take the smooth, that's like the smooth version, and then you take then you take the difference.
Yeah.
And then that could be decomposed into harmonics, right? Yeah. And then the frequencies are the Riemann, the Riemann zeros. But what I don't quite get is like, this is not it's not a finite domain, right?
Yeah, it's an exact formula from Riemann. Exactly, you can write these fluctuations as a sum. The variable it's not sine of t, it's sine of something like log t. I can't remember exactly, but yes.
Oh no, sorry. Yeah, okay. I get it.
Yeah, it's exact. And that was an amazing achievement of Riemann, among of course a number of others. There's a question there. Yeah.
You said that the classical counterpart of it could be a symplectic map instead of a continuous system. So what might that look like?
Oh God, believe me, indeed it could well be a map. We've thought of that. We haven't found one that works. We've thought of spin half. There are various hints that spin half might be involved with the Dirac equation because you get negative as well as positive. Yes, we have thought. Doesn't mean it doesn't work, but we can't make it work. Okay. Yeah. All right. Yeah.
Hello, can I ask a question?
Yes, Andre, go ahead.
Yes, I wonder if you mentioned the instantons at some point with values at integers. I wonder if this could have to do with the so-called Cramer's function, you know, which is a partition function over the, like a partition function over the summed over the Riemann zeros.
Yes, well, yes. Hello, Andre. Nice to hear you even remotely. Yes, the answer is I don't know. Remember that, of course, this is a refinement. I mean, this appears not directly in the Riemann zeros, but in the correction terms to the Riemann-Siegel expansion. When you beyond the least term of that. So it's a rather remote connection. But of course, well, and I didn't say it. Of course, XP, and this is probably in your mind certainly, XP is of course a rotation of x squared plus p squared, which is the ordinary harmonic oscillator, whose energy levels are proportional to m. So that's so I don't know if this relates to the partition function. And,
no, in fact, I read to Cramer's function in 1919, where you might say in your analogy that this Cramer function has poles at the negative integers, which would be like complex periods in your system.
Yes.
Of your
yes.
Okay.
But
that's
I don't understand the connection then with the Riemann zeros. But I know that there is a parallel body of work which involves statistical mechanics, and which is what you're thinking of. These are the Yang-Lee zeros. Is that correct?
No, I'm really thinking of that basic Cramer's function.
Okay.
Perhaps you might look at it again. It's published in 1919.
So if you write to me, I will be interested to hear about that.
Okay, I will. No, perhaps not today, but I will.
Whenever, yeah.
Thank you. I have to leave. I'm sorry.
Okay. I think
Bye-bye.
we do. So, okay. I think we're a little late, running a little late, but
I'm sorry.
No. It's my fault for talking too long before. So thank you very much to Michael again. Please could we show him our thanks. Now, I think there's time.